Alright, hey guys, what's going on? So today we are going to be talking about Mobius transformations. Now, Mobius transformations are super interesting. They're sort of the Lorentz analog to real space. But anyways, again, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to hit my Patreon page. If this is again something you're interested in, on the Patreon page, you will see exclusive content. You'll be given access to content early when stuff in this playlist comes out early. Right now, I'm just starting off this playlist, giving all this information out to you guys for free. And with that being said, let's get right into the topic. So we're talking about Mobius transformations. So Mobius transformations are super interesting. This is actually spelled like this. And we want to start off, I really want to put this in like sort of a no BS kind of way. A lot of times when you read about this kind of stuff, it can get really confusing. So this is going to be a fairly short video, and it's really just going to give you what you need to know moving forward, okay? So we are aware that transformations in R2, right? So we use matrices in R2 to transform things. When it comes to C, the complex plane, however, what we're going to find is that Mobius transformations are the most general transformations that we can think of in the complex plane. And this is going to be really useful again later on when we're talking about differential geometry. So we're going to consider the function that looks like this, right? So you might know already that this is the Mobius transformation, okay? But let's take a look at this a little bit more. We can split this, we can multiply the top and the bottom by C, just multiplying by 1. We can extrapolate out the numerator, and then we can split apart this now that because we have a common denominator for these. We split it apart in this way, where, and also I might add, we're adding AD and subtracting AD, so we're adding nothing to the numerator when we're doing this. And then we get to this point, and then we can factor out an A on this term, and we still have this term left. And then we can see here that we can cancel out these guys here, and we get AC plus BC minus AD, right? So BC minus AD over C times CZ plus D. We take the C out, that is C squared, but if we're taking the C out here, then we need to compensate that for dividing this by C, right? Because when we multiply this guy out, this is going to be C times D. So we need C times D here, so we need to divide that by C. So this is the Mobius transformation, just like this. It's just written in a different way. But the reason we do this is because now we can see how the Mobius transformation is really just a combination of translation, complex inversion, right? So inversion is interesting. We can dedicate a whole video on what complex inversion is. But then we have a factor of enlargement or shrinking and rotating with this factor, this green factor up here. And then we have translation. Okay. And so the Mobius transformation, this transformation up here is a combination really of just translations, inversions, and rotations. What do all of these things have in common? Well, they preserve angles and they preserve distances, right? So you can, whenever you rotate something, you're preserving distances. Whenever you're inverting something, you're preserving distances. Whenever you translate something, you preserve distances. And then at the same time, we are also preserving angles. So we note that when you translate something, you preserve angles. When you rotate something, everything within that rotation, if it's a continuous rotation, then you are also preserving angles. And if you enlarge something. Again, angles are preserved. And then we have another translation. So the Mobius transformation can be thought of as an isometry group. Right, so I'll write this down, isometry. An isometry group, broadly speaking, is a group of transformations. This is a group of transformations that renders whatever object you're transforming unchanged. Okay, that renders the object unchanged. So everything stays the same. Distances and angles are staying the same. So all of these types of transformations preserve circles also. This is something interesting to note. I don't want to go too much into this because a lot of the arguments regarding the preservation of circles really just have to do with the proof and the rigidity of motion that Mobius transformations give to the complex plane. There's a couple of videos on YouTube already about this kind of thing. Again, the point here is that Mobius transformations are isometry groups that preserve angles. In that sense, they're conformal, or conformal transformations, and they also preserve distances. Now, there's two types of isometry groups, and so one of the types is called a direct isometry group. And so when we're talking about isometries, there's two types. So we have the direct isometry, which preserves the sense of an angle. So you can imagine if you have an angle, say, I'll draw it right here. Here's an angle under a transformation that that angle stays the same. So this looks like there was a rotation involved. And then you have the opposite isometry group. The opposite isometry group reverses the sense of the angle. So this would be a reflection, right? So if I can somehow reflect this guy, this would look something like this maybe. Right, so we reflect about some axis, and the angle is still the same, it's just inverted, it's just reflected. This is important to note because the direct isometries, again, I don't really want to go into the proof here just because I think it would take too much time, and I think that would lend itself more towards exclusive content on Patreon, because I really just want to give you what you have to know if you really want to understand this kind of stuff. The direct isometries form a group. The opposite isometries they're a little bit more complicated in that they don't really form a group. You have to compose the opposite isometries with something else in order for the group, in order for it to be a proper group. And so the punchline here, so we've talked about direct opposite isometries, we've talked about the Mobius transformation and how it's really important in translations of the complex plane. We want to get to the punchline now, right? Because again, we're going over this book here. The book is, I actually don't have it with me right now, but the book is, I'll write it down, Visual Differential Differential Geometry and forms by Tristan Needham. I think that's how you spell his name. But we're primarily going through this book. It's a very good book on differential geometry. It really, I think, helps us understand it. We're on chapter 6 of this book right now. He goes through a lot. Chapter 6 is somewhat of a long chapter. He goes through a lot of proof. And I like how he goes through a lot of proof. But for the sake of, again, the time of this video, I really just want to get at the punchlines that he provides here. So the punchline here is that all three geometries that we've talked about so far, the Euclidean geometry, spherical geometry, and hyperbolic geometry, are all going to have, they all have constant curvature, as we've noted before, but they're all going to have isometries that are subgroups of the Mobius transformation. So let's remind ourselves that this is the Mobius transformation. And under Euclidean geometry, we have really this factor here. This is a rotation by some angle and a translation, right? So rotation, translation, that is a subgroup of a Mobius transformation. Okay. The reason this is a subgroup, sort of haphazardly going about a mental proof, seeing that this is a subgroup, is, well, it's got the translation, it's got the rotation, it doesn't have inversion, doesn't have reflection, right? So this is a group, but it's a subgroup of the Mobius transformation. Here we have spherical geometry, right? So spherical geometry is where the curvature was positive, greater than 0. In the stereographic map, again, we can conceive of other different types of maps for spherical geometry, but what we've talked about so far is the stereographic map of the sphere. The Mobius transformation looks like this, right? So in this, if we look at the transformation, C here is the negative complex conjugate of B, okay? And D is the complex conjugate of A. So, and then we're stipulating that A squared plus B squared equals 1. And we're going to see this. We'll go ahead and prove this in a few minutes. And then the hyperbolic, in the case of hyperbolic geometry, the curvature is going to be less than 0. Again, we've sort of gone over this before. And we've gone over this before, the Beltrami-Poincaré half-plane, where, and this is what the transformation is going to look like. This is really just a Mobius transformation. And we're sort of going to go over a haphazard proof as to why this is the case as well for hyperbolic geometry. So let's go ahead and do that right now. So recall, okay, so we're going to show this for the sphere, and then I'm sort of going to go over, again, it's kind of like a haphazard proof, again, just for the sake of time, but I really just want to provide you the punchlines in this video, sort of give you the no-nonsense, no bullshit kind of approach to differential geometry. So recall that for antipodal points on a sphere, this looks like this. So if we translate P, right, so this should be, I'll put a P right here. If we Mobius transform P, actually, I'll keep that as a, yeah, I'll say Mobius transform P you know what, actually I'll go Z, right, because if we Mobius transform Z, well, it's going to be equal to the Mobius transformation of this, okay, because that's right here, and by the concept of linearity, we can bring the Mobius transform to the numerator and the denominator, and we get something like this. So let's take this guy and let's do that Mobius transformation. So we're Mobius transforming this object right here. So when we do that, we get this. When we Mobius transform this object here, or when we do this transformation, we get something that looks more like this. And I don't think it's too difficult to see that, right? Because if you really just have to flip the numerator and the denominator if the whole Mobius transformation is in the denominator here. And so then we say, okay, well, these two are equal by virtue of working with antipodal points on a sphere. And when we do that, we equate these two things. Right, so this guy and this guy, bring them together. And then we get this, okay? So negative, negative, going to come out to be a positive. This negative here, we can bring it out over on this side. And so we get something that looks like this. And if we stare at this long enough, you can see that if C is equal to minus B inverse and D is equal to A, or not inverse, sorry, not inverse, the complex conjugate, D is equal to A, then it's clear that this whole thing actually becomes satisfied. And you can plug that in, right? So you're going to plug in C for everywhere you're going to put C, you're going to put this, okay? And everywhere you find D, you will put this, and then conversely, wherever you put C, wherever you find B, right, minus B, you can put that, and wherever you'll find A, you just do these substitutions, or so you do these substitutions, and what you get indeed is an equation that's satisfied. 1 equals 1, right? This whole thing actually becomes satisfied. And so therefore, the Mobius transformation, again, is this, right? Because we said that C equals minus B, right? So we actually have to put that, and then D equals, this should be an A, right? Okay, so this was the Mobius transformation. This is what we said right here. Okay. All right, and so like I mentioned, I'm pushing on 17 minutes here. For the sake of time, we're going to go through a more haphazard proof for the hyperbolic plane. And here's my haphazard proof, right? So since there's no restraining conditions such as needing to preserve antipodal points or anything like that on the Beltrami point-gray half-plane, because it really just is a plane, then the transformation is going to be the original Mobius transformation. Because again, the Mobius transformation is a transformation of the complex plane. The Beltrami point-gray half-plane is a complex plane, right? So a translation of a complex, transformation of a complex plane equals a transformation of a complex plane. There's no two ways about it. So this is sort of my haphazard way of doing this. There is a more rigorous way of doing this that I think will just confuse you, not confuse you guys, but it's something that I think would probably take more time for me to go through. So I'm giving you this sort of, again, like a haphazard proof, just to show that this is because this is the original Mobius transformation, because again, we're just doing transformations on a complex plane. The Beltrami point-gray half-plane is a complex plane. Okay. So let's sum this up. The idea here is that we have a complex plane, we have a complex sphere, we have a complex hypersphere, right? So this is the hyperbolic geometry, right? So hyperbolic sphere. I want to make this clear. Spherical geometry, hyperbolic geometry. So the mapping for hyperbolic geometry was mapping to the Beltrami-Poincare half-plane. Again, we looked at in detail what this half-plane was. As you increase, as you go up in constant values of the horizontal parameter, things get altitudes change, right? So these spaces down here are much wider than spaces up here, right? So this actually, when we get to higher and higher echelons of the hyperbolic geometry, these become skinnier up here. But anyways, so that this was the Beltrami-Poincare half-plane. This is a spherical geometry, right? So the spherical geometry was, our mappings, right? We're on this plane, C2, right? So this is C2 as well, right? So C2 right here, C2 on this half plane, and then this is just C2, right? This is C2. And so, in summary, the curvature for the plane is 0. Curvature for the sphere is greater than 0. Curvature for the hyperbolic plane is less than 0. And then we have our listed Mobius transformations as well. Okay. So, again, so we have a mapping to the hyperbolic plane. These planes, so these two guys are the same, and then this is where things are a little bit different. Okay. And so for this condition, also this condition, I didn't really go over this, but the idea here is that we want this to be a unit circle or a unit sphere. That's really where this comes from. Okay. And then this condition here comes from the fact that MZ, this is our Mobius transformation, is going to look like this, plus B over CZ plus D, and then M prime of Z equals this is actually going to be 1 over CZ plus D by quotient rule if this condition is met. Okay, so that's where that comes from, right? So this comes from showing a derivative, the actual derivative of a Mobius transformation. Okay, itself. But anyways, we have now sort of summarized Mobius transformations in our 3 constant curvature cases. And so with that being said, again, I hope you like this kind of content. If you like it, again, make sure to hit that like and subscribe button. Make sure to go onto my Patreon page where you can find exclusive and or early content. And with that being said, I will see you guys in the next video.